And our speakers are here. Today, Jules, Damji, and Amog Kamsetty will be talking about their presentation titled Modern Compute Stack for Scaling Large AI ML Workloads. Please welcome them. Come on up.
Good morning, or should I say good afternoon. Well, welcome to the last session of this particular track. Delighted to see so many of you actually here. I wasn't expecting that many, that you endured the heat and the all the cognitive load you have been attending the sessions. But delighted to be here. My name is Jules Damji, and I'm joined by my esteemed colleague Amog here. And today we want to share with you what are some of the modern emerging stack that are actually coming up to scaling your large-scale workloads. So that's going to be the talk of the session today. But before we get started, before we introduce who we are and what we work for and who do we work for, I just want to get an idea of who you are, where you come from. And so I want to just take a poll. How many of you actually have heard of Ray? Okay, you guys can stay, brilliant. How many of you are using Ray? Or if you heard of Ray, then you're probably using it. Good. I'm going to ask you a tongue-in-cheek question. How many of you have heard of a Hugging Face? It's like asking you, have you heard about Uber and if you're using it, you know? So delighted to be here. I think, just to introduce ourselves, my name is Jules Damji. I'm the lead developer advocate here at Anyscale. And prior to that, as part of the Ray team, prior to that, I worked in the similar roles at Databricks for about six and a half years. And then I was at Hortonworks. And prior to that, before I became an advocate, I worked as a software engineer at any of these, some of the notable companies. So I had the privilege and the honor to actually see the evolution of all these big revolutions that actually happened over the last 15, 20 years. And I'll have Amog introduce himself.
Hey everyone, I'm Amog. I'm one of the developers in the Ray team. We're also working at Anyscale. So I'm a Ray committer and have been working on Ray for past 3.5 years or so.
Brilliant, thanks Amog. Okay. So who do we work for? We work for a company called Anyscale, and Anyscale are the original creators of Ray. And Ray initially was created at Rice Lab. Anybody heard about Rice Lab? Okay, Rice Lab is a precursor to the lab at Berkeley called AmpLab. And AmpLab has been renowned to create some of the great open source software which led to companies funding them. One is Spark. Anybody heard about Apache Spark? Okay. Mesos was another one of them, Tycon. So these are some of the projects that actually emerged from the, and Ray is one of them. And what do we do? What does Anyscale do? We provide you the managed service, provide you the compute strata for your ML workloads. And why do we do that? The reason is that if you actually are working in the ML and AI workspace, distributed computing is a necessity. It's no longer a norm. It is actually a must thing today. You can't really do things today at the scale that machine learning workflows actually require and AI workflows require. So our vision has been to make that simple for everyone, for any Python developer who can actually scale the machine learning workloads. So that's what the company actually worked for. And so here's the agenda for today. Here's the lay of the land for the next 25 minutes. We're going to share with you some of the challenges that developers are facing today to scale the machine learning workloads. Because machine learning workloads are very diverse. They incorporate a lot of different frameworks, and they're varied in the demands and the use cases. So what are some of the challenges with respect to the infrastructure that you actually require that? And then we will talk about mainly how the emerging stack today of LLM is sort of making waves, and how Ray addresses those challenges for developers as well. And then we actually will give you a more specific case, how you can actually take a Hugging Face large language model, tune it using Ray AI transformers, and you use Ray AI for that. So that's going to be sort of the grand scheme of things. But here are some of the challenges I want to sort of talk about with you. We hear from developers today that training takes too long, right? It takes too long because either the data is too long, it doesn't fit in one load, so we have to somehow distribute that particular data, so you have to worry about those things. Models are large. They don't fit on one particular machine. We have to distribute them. We have to shard them. There are too many frameworks which are actually coming up at the pace, and we have to sort of get into the mode of updating of infrastructure all the time, because ML is moving at the pace as you know today. So those are some of the challenges that we actually faced and how we can actually address that. And if I had to sort of visualize those pictorially, what you're actually seeing over here is a typical ML pipeline that most developers today who are actually dealing with ML workloads pipeline deal with it. So here's a very simple case. You have a diagram where you actually have three things actually happening in the pipeline. You have Apache Spark, which is actually being used to read large amounts of data from your data store. It could be data lake, it could be S3 bucket. And you're creating, pre-processing that in a distributed manner, and you're creating some cleans data which you're fitting into your TensorFlow, probably running on Horoword in a distributed manner. And once you've actually done that, you have created your training data and evaluation data, and now you're actually going to do evaluation in a distributed manner with TensorFlow. And most likely, some of you might actually orchestrate that using, orchestrating tool like Airflow. Now here in the very simple case, you have a situation where you have three disparate distributed systems. You have to manage them. You have to deal with infrastructure. You have to monitor them. And if you are a developer and you have to deal with these things, your developer velocity is going to drop considerably. And if the infrastructure is changing, now you have to worry about that this infrastructure had to be updated. So that's the one challenge where you actually have bespoke distributed systems that you have to worry about stitching together and make sure that they orchestrate and they work well together. So that's challenge number one. And if you were to do this in production environment, you can actually imagine what your staging environment looks like and what your desktop looks like. You can't really replicate on your desktop. So that's challenge number one. The challenge number two is that today the pace at which the ML domain is actually changing, and the testament of all the LLM models which are being developed on weekly basis and hourly basis, we keep on hearing about those things. You want, as an ML developer, the latest technology. You want the state-of-the-art algorithms, the state-of-the-art machine learning frameworks. So how do you do that, right? The problem now is that if a new framework comes out, you run into the problem of saying, okay, I have to update that. And so you constantly get into this fatigue, I call that, the fatigue of updating. It's like being on a hamster wheel. You just keep on updating those things. And that sort of affects your general pace and developer velocity that you actually do that. And if I had to somehow summarize that in terms of the cascading of the root causes that actually create that, you can think about on the left-hand side, you're a data scientist, you're an ML developer, you're a machine learning, you want your machine learning algorithm to work quickly, you want to build your model quickly. And so one of the things you might suggest to your infrastructure group is, why don't we just go with the vendor solution, right, that addresses some of the provisioning of the clusters, and we can actually use a specific framework they allow. Well, that's a good solution, but the problem over there is that you might be tied to a particular vendor that might be tied to a particular framework. And so if there are new frameworks come up, you are somehow at the loss. You are beholden to their pace at which they can actually do the velocity. Or you might say, well, let's go ahead and build our own infrastructure. That has its own problems because not many people actually have the capacity and the expertise to actually build large infrastructure. So, companies like Google and Netflix and all that, they have a dedicated SRE teams whose existence is nothing but to build these particular systems for the ML engineers. So you have this cascading of those things to deal with. And what we want today really is the blessings of scale that exist today, because we want to be able to take advantage of all this infrastructure that's available to us, that we want to scale it. We want the blessings of scale, and we also want the simplicity of yesteryears. And I'll get into the analogy, what I mean by the simplicity of yesterday. And we want to reduce the developer velocity. We want to manage, we want to ensure that this infrastructure is automatically scaled. Somebody is actually dealing with it automatically, or the framework you're dealing with, the compute strata does the scaling for you. And you want to have a single framework in which you can actually do your end-to-end pipeline. In other words, you should be able to do your data ingestion, you should be able to do your training, you should be able to do your tuning and inferencing and so on and so forth. You can do them collectively or you can do that individually. There has to have the flexibility. So how do you do that, right? We want the simplicity of yesterday. 2010, you could do that, it's very simple, right? Life was simple, things were simple, models were simple, data was small, right? Everything just fits in one particular computer. You download your particular scikit data from somewhere, you pip install scikit, you do the transformation, right, the fit transform, whatever scaling you actually want to do. Once you've done that, you do a fit training, and then you do the evaluate. Very simple. Everything is actually done in one single script. That doesn't work today, right? That doesn't work today because, as I said earlier, that models are large, frameworks are more complicated. People actually want to be able to scale those things because scaling is a necessity, not an exception. And what we really want, that we want to covet the simplicity of yesterday, but the blessings of scale today. And how do we do that, right? We want to be able to actually pick up any particular pre-processing data that we actually want. We want to be able to read data from any of the data stores that we have using any of the file formats that we actually want to be able to do that in one single script. We want to be able to select the frameworks of today which are state-of-the-art. We want TensorFlow, we want PyTorch, we want JAX, we want Alpha, we want all these new frameworks which are coming up that allow us to do large model building. And we want to be able to do that rather seamlessly. And then finally, once you have done that, we should be able to actually do the inference and scaling, and all then can be actually written that in one single file. And our contention, opinionated as it is that you can actually do that with Ray AI. So what I mean by that, but before I talk about Ray AI, I think it's important for me to talk about what is Ray. And that was one of the questions that I wanted to sort of address. So we can think of Ray as a single purpose distributed framework that allows you to scale your machine learning workloads across a large cluster. It's not only specific to machine learning, but we focus on that primarily, but you can also scale your Python workloads. So if you actually have a Python application that you want to distribute across, you can actually do that. And it works on your laptop, it works on Kubernetes cluster, it works on any of the public cloud loads. And more importantly, I think I like to see it visually as a layered cake of capabilities and functionalities that you actually have. So if I were to actually look at this particular diagram, at the bottom you actually have the cloud on which Ray actually runs. And as you go one level above, you have the Ray core, which are the primitives that we actually provide you for you to write your distributed application. And those primitives are such as tasks, which you can take your Python functions and convert them into a task in a distributed manner. You can take classes that you have, Python classes, and convert them into actors, which are stateful operations that can run distributed across. And we have object stores, which are just sort of distributed store that you can actually store data and retrieve them back and forth. And as you go up or level, Ray AI is actually built on top of Ray. So that gets the benefit of scaling, fault tolerance, memory management. All that is actually done for you. You don't have to worry about that. You just write Python code, and everything is actually done for you. So Ray AI is actually built on top of that. And if you're on the far right, that you don't care about being a machine learning developer, you are a Python programmer who actually wants to scale your machine learning workloads, you can just write those, using those primitives, you can actually write to scale your Python applications. And you might ask, well, who's sort of using Ray today? Why Ray has been gaining the momentum in the machine learning space? And you have these notable companies who are actually using Ray at a massive scale. And for those of you who are familiar with the LLM workspace, which is really taking of imagination, companies like OpenAI, who built the early GPT-2s and GPT-3 and ChatGPT-3 using Ray, and Cohere is another one that actually provides the platform in generative AI actually use Ray. And there's all these notable companies who are actually using Ray. And it has been fortunate to gain this momentum from the community, because you have the validation of all these companies who are actually using this open source version of Ray to build not only their platform on top of Ray, but also scale the individual workloads using Ray as well as Ray AI. So let me talk about briefly what is Ray AI. You think of Ray as a toolkit. So we have all these libraries which allow you to do individual workloads. So if you have a data set that you actually want to read from a particular repository or a certain file format, you can use Ray data for that. And it allows you to distribute your data, it allows you to shard your data, and feed that into Ray Train. And Ray Train is your training library that allows you to train your models at scale. Whether you want 25 models to scale or you want across the entire cluster. If you're training, you also might be doing hyperparameter tuning, right? So tune is another way to actually use that particular library to tune your particular model. And if you're using serve, once you've trained your model, well, you've created a checkpoint, and now you actually want to deploy it, Ray serve allows you to deploy that. And if you are in the reinforcement learning domain where you actually want to build large rec systems or you want to build large games, RLlib is one of the popular libraries that allow you to do reinforcement learning. And all these libraries sort of work very cohesively together. They're very declarative, and they provide you sort of base classes so that you can actually now extend and do customization as well. So that's sort of at the bottom level. Because it's built on top of Ray, it gives you the scalability that Ray that provides you. If you go up, there are built-in integrations that come up with, right? So Ray Data actually can work with any of these libraries they actually see in that particular blocks. And I know this is a marketing diagram, but the idea is that Ray Air integrates with all these libraries. And because it actually provides you this built-in, straight out of the box, you can actually use that. And there are some community versions which are supported. So some of the diagrams you actually see are there. So the classes for each of these components are written in such a way that you can actually customize and extend that. So that sort of gives you the ability to customize things. So if there's a new framework that actually comes out and you need to incorporate that, you can actually write the customization very easily. And that sort of provides you the future proof, right? You don't get into that hamster wheel that I was talking about, that is the constant fatigue. Oh, this new framework, Alpy has actually come out, or JAX has come out, and I really want to be able to actually use that JAX trainer and compiler with my model. How do I do that? Well, you can actually extend the base classes for the trainer, and you just write the training function that JAX will actually run, and we do the distribution for that automatically for you. So that's one of the beauties that gives you the future proof. So you might ask Jules, when do you actually use Ray Air? Well, there are 4 scenarios in which most of the developers over here, or people who actually are building ML applications end-to-end, will use it. One is they want to be able to do a single workload. So if I just want to do data ingestion, for example, and I want to do some transformations, last-minute transformation at scale, as we saw in the first diagram in the challenges where we had the Spark and we were reading data, we just want to take that particular data, ingest it into our trainer. So people would actually do that. Or you just want to do train. You don't care about, you already have your data sitting in Delta Lake or in Lakehouse. It's already clean, everything is structured, and you want to use XGBoost to load that particular data, and you would Ray Data to actually do that, and you feed it to your trainer. And trainer could be something that you actually want to distribute the manner. Or you don't care about trainer. You already have a trained model, but you want to further tune it, so you can actually use tune for that matter. So that's if you want to use individual workloads. If you want to build an entire end-to-end application, as we saw in the other diagram, where you're actually doing data ingestion, you're doing training, you're doing tuning, and then you're doing batch inference. That allows you to be able to do that. And once you've done that, you actually want to deploy it and you want to serve it. Or you have existing ecosystem libraries such as Hugging Face, which is integrated with Ray Air. You want to build a particular model, or you want to fine-tune an existing LLM model. And that's the case that we're going to explore today, which is an existing ecosystem of libraries integrated with Ray Air, so you can actually do things for your use case. And then finally, you want to build a platform on top of Ray, right? And so the companies like Uber, and the companies like Netflix, and the companies like Instacart, and Shopify, and Spotify have built the entire platform on top of Ray. So if you actually are one of those companies who actually want to do that, that's where you actually would actually use Ray. And so now I'm going to hand over to Amog, who's going to now deep dive into each individual component, and then we'll get into the demo.
Thanks, Jules. So, let's deep dive into each of these Ray Air components. And just to reiterate one of the points that Jules made, you can think about Ray Air as something like Google Drive, right? You have this Google Drive, which contains a suite of different components. You have docs, sheets, slides. Each of them can be used individually. If you want to just do Google Docs, you can just do Google Docs. But if you use the entire thing, they all interoperate very cleanly with each other. So a similar concept with the Ray Air. There's multiple different components for different types of workloads. But if you want to do the full machine learning workflow in a scalable fashion, all these different components of Ray Air interoperate very easily with each other. So you can go from development and data processing to training to then like production and inference. So the first component that we have is Ray Air's data ingest, right? So for any type of machine learning workflow, it all starts with the data. And the problems we're seeing today is data is very large, right? You're dealing with hundreds of gigabytes, terabytes, petabytes of data for training the complex models that we have. So this is where Ray datasets comes in. So Ray AI uses Ray datasets, and this is one of the components where we can basically make it very easy to scale out data ingestion. So reading data from a variety of different file formats or from a variety of different sources in a distributed fashion, being able to process that data and parallelizing it across thousands of cores in your cluster, all in just a few lines of code. So now that you have your data ingested and loaded into your cluster, now you want to process that data. And this is where Ray AI's preprocessors comes in. So you can see like the API is very similar to scikit-learn preprocessing, right? So you basically define some sort of preprocessor. You can fit that preprocessor on some data set. In this case, it would be a distributed data set, and then transform that data set. So we take the same API as scikit-learn, something simple, something that people are familiar with, except all of this code can run in a distributed fashion. So whether you have 50 nodes, 100 nodes, however large your cluster is, this exact code right now, you can just basically run this on very large data, and it will parallelize across all your CPUs in your cluster. So this is kind of the type of experience that Ray AI provides, that it abstracts away a lot of the scaling and distributed complexities from your workflow. And as a data scientist, you can continue to just work as you were with scikit-learn, except now processing large amounts of data. So once we have our data processed, the next is we want to do scalable model training, right? So again, with the amount of data we have, as well as the model sizes, training on a single GPU, training on a single node, probably is going to take hours, may take days. So what we want to do instead is that we want to use Ray AI to scale out the training process. And Ray AI also integrates with the best-in-class open source tools, right? So you can, if you're using Hugging Face, you can continue to use Hugging Face, PyTorch, and so on. So you can single API to scale out your ML frameworks, seamless integration with other libraries. And this is just an overview of how the parallelization works. It's pretty standard, like data parallel training, but also we have we integrate with optimizations for being able to train larger models that don't fit in a single GPU. You can handle lots of data and abstracts away a lot of the complexities that you may see. Then once you've trained your model, you want to do hyperparameter tuning, and this is where RayTune comes in, right? So again, when you're training your model, you want to try out different hyperparameter configurations, and you want to run the whole thing in parallel across the entire cluster. So you can use RayTune and simply, again, with like a few simple lines of code, parallelize your entire hyperparameter tuning experiment. We also integrate with the best logging and monitoring tools. So as you're doing your hyperparameter tuning or as you're doing your training, you can log all the results to weights and biases, MLflow, TensorBoard, so on. So you can visualize and track your experiments. And then finally, once you have your trained model, now you want to do inference. And again, when you do inference, you want to do it at scale, right? So there's two different types of inference that we support. One is the offline case. So you have a bunch of data, you have a trained model, and you just want to get inference on these different data, on this data set that you have. So this runs as like an offline job where, again, the data set could be gigabytes, terabytes level size, and Ray AI can parallelize the inference across your entire cluster. And the second case is the online case where you actually have a human in the loop and you want to deploy this trained model into as an actual service that users are interacting with. And again, if you have a lot of users or a lot of requests coming in, you want to be able to parallelize and scale so you can handle the load. So this is where Ray Serve comes in. So you can take a trained model that was trained with the Ray Train and deploy it with the Ray Serve for scalable and fault-tolerant inference. So what are users saying about Ray AI? I think this is just one quote we have from an ML engineer from Spotify. But what he's saying is that Ray AI enables them to develop end-to-end machine learning pipelines. And really the beauty here is that you can take the same simple APIs, right? Like referring back to the analogy that Jules showed, take the same simple APIs that you might be familiar with scikit-learn and use those same APIs, use the same user experience, except now do this in a distributed fashion. So it allows you to develop at scale. It provides very embarrassingly parallel workflows. It provides a very easy user experience. And makes it easy to, because you're developing at scale, now that we want to go to production, you can easily go from development to production. There's very little friction there. Cool, so I think we had this demo here, but running a little bit short of time, so maybe we'll just leave it open for questions right now, and then I can show you the demo afterwards if you like.
There it is, actually, ray tuning. Go to NumFOCUS.
Maybe this one?
And then start.
Any questions from the audience? Please come to us at the front. We're chairs, we don't walk.
We don't want to hold you back between lunch.
So I have a question.
Yeah.
So you showcase how Ray integrates with many of the tools we might be familiar with, regardless of which we have chosen. But you didn't go into the interesting part of what makes it scale so well, right? Is there a principle into the articulation of the distributed computing as implemented by Ray that makes me want to prefer it over, say, a Dask cluster? Because Dask clusters are easy to just spin up on my machine. So is there a reason for which I should care and prefer it?
Yeah, so I think like basically, let me just go back to one of the previous slides. So as you can see, like we have the Ray AI Runtime, and the reason why it scales so well is because like it's built on top of the Ray core, right? So Ray core provides a lot of the primitives for being able to scale out Python functions or classes across an entire cluster. And we can go a little bit more into technical details, right, compared to Dask. Kind of there's a little bit different design principles, for example, how we do scheduling versus how Dask does scheduling. So Dask has a centralized scheduler, Ray has a decentralized scheduler. Also kind of different nuance, a little bit other nuances there as well. Like Ray has like a distributed shared memory object store, so it makes it very easy to have, essentially you can think about it as having unified memory across a large cluster of nodes. So those are the kinds of like technical details that Ray core provides, and because Ray core provides that, Ray AI Runtime can build on top of that to provide easy scaling, but with also a very easy to use API.
So that drives me to a follow-up question. Does that mean that the worker processes that make up the distributed computing pool are not strictly quoted in terms of the RAM they use on each compute node?
Well, I mean, when you actually create a particular cluster, right? Oops. So when you actually create a cluster, the worker nodes are tied to each and every CPU. So if you actually have 7 nodes and each of them had 8 cores, you'll have that many workers. Each worker process is tied to a particular CPU. And so when you actually create a task to be scheduled, it can be scheduled on any one of those things, right?
No, I get it, but it's the memory separation. So
Yes.
it's a problem I encounter constantly with my Dask clusters. I have a thing that grows as it goes through my compute DAG, and at the end node of it, it becomes too big for a single worker.
So what happens at that time? We have this notion of auto scaling. So once let's say you create your cluster.yml, if you're using open source, you've created 10 nodes. And now your workload has maximized across all those 10 nodes. And now you actually, your work queue is actually being queued. We have auto scalers which will actually create automatically 2 or 3 more clusters for you, nodes, and then it will distribute those remaining tasks over there, and it will scale down when the loads finishes. So there is an auto scaling capability of growing horizontally and then shrinking back depending on the traffic of the workload you have. I'm assuming that, and so that would take care of your memory constraints that you actually have, because you can't really add memory on the fly. You can just add nodes as they go on to scale it across. So initially, if you create 5 nodes, and somehow 5 nodes are too little, you can actually tell that go ahead and scale it to about 10 nodes, and it will automatically scale incrementally.
Okay, thank you.
So I do want to actually just challenge that question a little bit. I think like if you're a data scientist or an ML person working in machine learning, you shouldn't need to care about the memory or the worker processes. Like these are like lower level like distributed system concepts. So if you're using like Ray core, like yes, if you want the lower level flexibility, you can do that. But like the idea that we want to show is that, hey, like you don't need to care about these things, right? Like you use Ray train, you use Ray data to very easily do this types of very complicated tasks, but without having to worry about the memory or the workers or processes or things like that.
Okay, I'll take you up on that,
Yeah.
and I'll write to you personally when it breaks.
Please do so. Any other questions? Yeah, we're going to hang around here if you actually want to see the demo, because we don't have. Oh, go ahead.
So I have a cluster which is, I believe the polite term is organic. How tolerant is Ray of extremely heterogeneous hardware substrates?
Yeah, so I think currently we have like native support for CPUs and GPUs, but we also have the support to be able to add different instance types or different type of resources, like be able to, for users to be able to add those, right? So there's an API that you can like interface and be able to add that type of support. But the native support is on CPUs and GPUs. Yeah.
And currently the GPUs are the NVIDIA CPUs. So if you actually want to, for example, Cohere uses TPUs, so you can actually use TPUs as well. But we'll have to have the underlying support for that.
So please follow up with our speakers if you have further questions on Slack. For the time being, this is the end of the ML and data science and AI in ethics track. Thank you so much for your participation, and let's go have lunch.
Thank you.
Thank you.